incendiary forecast for the next 24 hours.
Hello, very good morning to you and welcome to the 60s.
Our planet is filled with signals invisible to the naked eye.
1, 0.
But space itself can be just as noisy. This is Cambridge University's Radio Telescope Observatory. It's used to examine the far reaches of space, to answer questions about the very origin of our universe.
These magnificent dishes are detecting signals from radiation left over from the Big Bang. But they're not optical telescopes in the sense of looking through an eyepiece and seeing out a planet or a star. These dishes are detecting radio waves.
These telescopes allow us to see the unseen. Extraordinary images like these are made possible thanks to radio waves, microwaves, and gamma rays.
The thing is, all these waves are connected. They're all different types of something we call electromagnetic radiation. Visible light, the light that you and I can see, is just a tiny portion of this broader spectrum of waves. And we use waves to probe the outer reaches of our universe. But we use them for so much more.
In fact, electromagnetic waves are at the heart of modern technology. We use them every day in everything from medicine to communications.
That's a man's face. There it is. There it is.
Our mastery of these waves was made possible when one man published a set of equations in 1865. A man called James Clerk Maxwell.
His name's barely known to the public, and yet he's probably the finest scientist Scotland's ever produced. And 150 years after his greatest discovery, I'm setting out to explore the story of the man and his work. Excuse me, can I ask you a question? Do you recognise this person? No? Do you know who he is?
Alexander Graham Bell?
No idea.
He looks like a banker, an economist maybe?
James Clerk Maxwell. Still no idea?
Still no idea.
James Clerk Maxwell.
Never heard of him.
Albert Einstein or something. No.
You're so close! James Clerk Maxwell. Name ring a bell?
Maxwell's equations?
Maxwell's equations.
I don't know what they're about, but I've heard of them.
Right, you do physics?
I do physics.
Okay, James Clerk Maxwell, and this is your test.
I just failed physics.
That's a statue. It's a statue. That's a statue. Oh, you probably pass that quite regularly.
Quite regularly, so it's quite an embarrassment to say.
No, but no one. I've been asking everyone here. James Clerk Maxwell. No one knows who he is. Any ideas? This is a statue of James Clerk Maxwell. And yet virtually no one around here knows who he is. But I don't blame them, because Maxwell seems to have slipped through the cracks of history, at least as far as the public's concerned. So who was he?
James Clerk Maxwell was a 19th century Scottish scientist. He used his genius to work across a wide range of subjects. Astronomy, physiology, colour, optics, thermodynamics, electricity and magnetism. He touched on all of these and changed many of them beyond recognition. He caused a revolution in physics and gave us the laws for one of the four fundamental forces of the universe. Einstein kept a picture of Maxwell on the wall of his study and once said, "I stand on the shoulders of James Clerk Maxwell." It's a sentiment shared by many physicists today.
Maxwell did for electricity and magnetism what Isaac Newton did for gravity.
He's one of my great heroes. He's one of the greatest scientists we're ever going to encounter. He's on the par with Einstein, with Newton, with Archimedes. He transformed our way in which we understand the world.
He's probably the greatest scientist Scotland's ever produced. And we're still living in the shadow of his achievements, and yet no one knows who he is. Even me, a Scot and a scientist, just got this vague notion of what he did. But I want to change that. I want to rediscover James Clerk Maxwell.
Born in Edinburgh in 1831, Maxwell was the only child in a landowning family from Galloway. The scientific revolution of the previous centuries was changing our view of the world, but modern science was still in its infancy. The 19th century would see groundbreaking discoveries, and Maxwell would be at the heart of it, compelled by a probing mind. His inquisitive nature was obvious, even in childhood. When he was a boy, the zoetrope was a new invention, and the young Maxwell loved them. It's kind of hypnotic. In a sense, these are the forerunners of movies and television, and you can imagine kids in the 19th century just being mesmerised by them. Most of them would have been happy just to sit back and enjoy the show, but Maxwell wanted to know how they worked. The moving figures are a trick of the eye. Stop the drum spinning and you can see the simple sketches that help create the moving image. This simple illusion captivated Maxwell. As a child, he would build his own zoetrope strips to entertain his family and to understand how they worked. This desire to understand the world around him continued into adulthood. Aged just 14, he produced a paper on geometric shapes that showed such mathematical ingenuity it was published, and then read at the Royal Society of Edinburgh by an established professor, as James was deemed too young. As a teenager, he conducted homemade experiments into light and colour. And by the time he arrived at Cambridge University, aged 19, he'd already published 3 mathematical papers. From the age of 14, Maxwell had been using mathematics to explain how the world worked. It was a talent he would rely on for many of his discoveries, and it was key to establishing his scientific reputation. Because while still in his 20s, he used maths to solve a riddle that had puzzled scientists for centuries. Strange as it may seem, in Maxwell's time, we didn't really know what colour was, or why we saw colour at all. In the 17th century, Isaac Newton had given us food for thought. By using a prism, he had split sunlight into separate colours, the familiar colours of the rainbow. He showed that what we perceive as white light is actually a mixture of different colours. Newton said that every colour we see was a result of mixing the colours we see in the rainbow. He tried and failed to establish the rules of mixing. 150 years later, we weren't much wiser. Maxwell was interested in colour and why we perceive it throughout his life. And his first real breakthrough came as a Cambridge student. Artists seem to be ahead of scientists on this. For centuries they had been creating a vast palette of colours, often by just mixing red, blue and yellow. Artists refer to these three as the primary colours, and using them they could create entirely different colours.
So if a painter was mixing red and yellow, he would get orange. And if he was mixing blue and red, then he'd get purple. But if they were mixing blue and yellow, then they would get green.
As a student, Maxwell read about the work of Thomas Young. Young thought that there was something significant about the number of primary colours. But he also thought biology had a role to play.
Young argued that the human eye had 3 receptors in it, each one sensitive to a particular colour. He argued that the brain worked like a painter, combining messages from each receptor to build up this perception of colour. It's a stroke of intuitive genius. We just didn't have any proof.
Young thought that these receptors corresponded to the painter's primary colours. Taken by Young's 3-colour theory, Maxwell wanted to test it. He devised a way to mix the primary colours with mathematical precision. He then tested those mixtures on a wide range of people to see if they all perceived the same colour. And he did this with a deceptively simple tool.
So this looks old. What's this then?
This is Maxwell's original colour wheel, which we are very pleased to have in the laboratory.
So that's the original thing.
This is the original thing. That's it. It's slightly beaten up. It's been used a lot. And that's because Maxwell used this to test out the mixing of lights among all his friends when he was here in Trinity College. It is pretty antique, as you can see, but the idea is you put different amounts of the coloured papers here, and then when you rotate them, then they mix up. And this works because of the typical time that the eye can respond is a 20th of a second. And so if it goes faster, the eye will interpret this as the mixture of the colours.
And this is a motorised version, is it?
This is a motorised version of it, and we can actually demonstrate how the colour mixing works with this rather pretty demonstration here. We were going to mix red and blue. We'll rotate it rapidly, and then we will see which colour we produce.
Just like his childhood zoetrope, Maxwell's colour wheel would spin so fast it would trick the human eye.
So if you were going to bring up that light...
This one here?
That's right. So
instead of moving figures, he'd be mixing colours just as artists did, but with mathematical precision. When he mixed red and blue, he got the same colour artists did when they mixed paint.
And that's kind of magenta, purple.
Yes, it's a sort of a magenta colour.
If Young was right, and there were receptors in our eye that responded to the artist's primary colours, then perhaps mixing red, yellow and blue in equal measure would produce white. But it didn't. So Maxwell tried different combinations.
We can begin now to reveal green as well as blue here. And if we just do a little bit of fiddling around with these discs, we'll be able to get equal amounts of red, green and blue, and we can then see what colours we observe. Okay?
So it's white. I mean,
it's white.
It's the only colour you call that, white.
So this is a beautiful demonstration of the fact that the primary lights, and notice the word light, not pigments, the primary lights are red, blue and green. And you can create any colour of light by suitable mixture of different proportions of these. What happens in paintings, pigments absorb light, whereas this is emitting light. So the upshot of all of this was that Maxwell was able to produce a rather beautiful colour triangle diagram, which could indicate how you would create any colour by mixing the 3 primary colours.
Maxwell's colour triangle allowed him to pick a specific colour and work out how much of each primary colour would be needed to reproduce it. This was made possible by his mathematical precision and systematic testing. Maxwell's work swept aside a sea of confusion. He vindicated Young's theory and demonstrated that we see colours in paints differently to the way we see colours in light. He established the primary colours for light as red, blue and green. He realised the receptors in our eyes were sensitive to those three, and that by mixing them we perceived a vast range of colours. A few years later, he provided a stunning display that he was right. In 1861, Maxwell was invited to the Royal Institution in London to give a lecture on colour vision. But he didn't want to just talk about the principles. He wanted to demonstrate them to his audience. What he did would astonish them.
Maxwell took 3 photographs of the same object. Each photo had a different filter on it. One was red, one was green, and one was blue. That gave Maxwell 3 photographic plates that he could use to project an image with.
When Maxwell projected the image from the red photograph onto the wall, he got a red picture. In an age when photography was black and white, this was interesting, but hardly revolutionary.
But if you project all 3 images onto the wall at the exact same spot, something special happens.
The audience were looking at the world's first colour photograph. They were stunned. Maxwell had chosen the perfect subject for his picture, a brightly coloured tartan ribbon. By layering red, green and blue images on top of each other, Maxwell established the possibility of creating colour photographs. 150 years later, we use this method daily because this 3-colour principle is used in colour TV, computer screens, even mobile phones. The colours we see on our screens, however big or small, are created by carefully mixing the primary colours. Maxwell's work on colour provides the basis for our present understanding of colour vision. He even proposed an explanation for why some people were colourblind. He said the receptors in their eyes were faulty, and that this radically altered how they perceived colour.
3 weeks after his colour show, Maxwell was elected to the Royal Society for his work on Saturn's rings and on colour. He was now counted amongst the finest physicists in Britain, and he was 29.
Maxwell arrived in London at the end of 1860 and assumed teaching duties immediately. While there, he focused on a subject that had captured his attention many years before.
Ever since his early days at Cambridge, Maxwell's been interested in electricity, after it was suggested as an area to look at by a friend.
That friend's advice was simple. If Maxwell wanted to learn something about electricity, he needed to know Michael Faraday. Faraday was a self-taught scientist who was revolutionising our understanding of electricity and magnetism. Maxwell's relationship with him was one of the most fruitful in 19th century science. We'd known about electricity and magnetism since ancient times. Most people had experienced the power of electricity through terrifying lightning storms. And we'd used magnetism in ships' compasses for centuries. They were considered completely separate things for most of our history. But in the early 19th century, scientists like Faraday were beginning to see a mysterious connection between the two. Deep in the heart of the Royal Institution, Faraday conducted experiments to understand how they were linked. In one experiment, a copper wire carrying electricity somehow provoked a nearby compass to move. In another, Faraday tried to do the opposite. Use a magnet to generate electricity.
Which led him to invent the electric generator, of which this is an example, where you have a permanent magnet and a coil of wire.
So the wire is wrapped around this bit inside.
The wire's wrapped around a cylinder, and you push and pull the magnet in and out of the cylinder to generate an electric current.
I like the lights. What's the Christmas lights for then?
Well, that's to show the electricity is passing.
Oh, okay.
Faraday did not use light-emitting diodes.
I think he should have done. That was his great mistake.
And all electricity power stations throughout the world use this principle of generating electricity that Faraday discovered down here in 1831.
Faraday had generated electricity simply by moving a magnet through a coiled wire. A discovery that would forever be associated with his name. But he was left with perplexing questions. There was no physical contact between the electric wire and the magnetic needle that moved, nor between the moving magnet and the copper coil. They were affecting each other through seemingly thin air. But how could that be?
Now, what Faraday thought was happening was that there were lines of force coming out at the end of the magnet, which were then cutting the wire within the coil to move electricity around the coil.
The idea of mysterious lines coming out of the magnet to generate electricity may have seemed outlandish, but Faraday had a simple experiment that could prove their existence.
So he took a very powerful permanent magnet, placed some paper on it, sprinkled iron farthings over it, just to represent the lines of force.
It never fails to impress that.
Of the magnet, and you can see the sort of three-dimensional
So these
structure.
These are coming up here and swinging around,
that's
and then
right,
coming down into this bit here.
And Faraday sort of made permanent examples of this and sent them around to all his mates in Europe to show that space had structure, as a very strong argument for his field theory.
So Faraday thought there was an invisible force field at work here.
Literally a field. I mean, Faraday still brings the word field into science, and it's invisible, as you say. But so this is why this is just a representation. It shows the existence of those invisible lines.
Faraday's iron filings experiment revealed the existence of an invisible field stretching out into thin air. These fields, he thought, were responsible for the experimental results he'd seen. Despite having physical proof, Faraday lacked a mathematical description of how the field was generated, or why it affected things around it. Without a mathematical proof, many 19th century scientists dismissed the theory as speculative. But Maxwell had followed Faraday's work for years and set out to prove him right. Maxwell had plenty of time to mull over the problem. The walk from his Kensington home to King's College was an 8-mile round trip every day. And during the walk, he allowed his mind to wander. On those walks and at work, he had company.
Apparently Maxwell always had a dog, and he always called it the same name. From childhood onwards, every dog was called Toby. And Toby, whichever one it was, rarely left his side.
Toby was a constant companion at home and in the lab. It's a sign of Maxwell's eccentricity that he would talk to Toby. He said he liked his company. During his walks to and from work, Maxwell, and perhaps Toby, brooded over the mysterious relationship between electricity and magnetism. His aim was to provide a mathematical explanation for the link between the two. After years of thinking, and who knows how many miles walking, he came up with a set of equations that described the relationship between electricity and magnetism. Equations that would change our lives forever.
Sorry, Frank, but this is just gobbledygook to me. I'm just looking at it, trying to make sense of it.
Well, it's not much easier for me. I mean, that's what he wrote first of all, and looking at these, they probably mean little more to me than to you. But 20 years later, they were written in a simpler form, which is the way that
this way here.
This form here.
That looks more manageable, but it still looks a bit confused. Could you take us through it then?
Right, well, the first one says that if you've got an electric charge, it spreads an electric field out all over space.
Just like his work on Saturn's rings, each equation is a mathematical description of something observed in the real world. So the first equation described how a static electric charge generates an electric field. And the second, that magnetic poles always come in pairs. The third equation describes how a changing magnetic field generates an electric field. And the fourth equation, that an electric current surrounds itself with a magnetic field. But Maxwell realised there was something missing.
Maxwell's genius was to realise that each of these equations is fine until you put them together. Mm-hmm. And then he realised something was missing, and it was in this final equation. He said, there has to be another term. And what this extra piece says is if an electric field is changing, it will surround itself with a magnetic field.
Right.
Which is like the sort of mirror of this equation, which says if a magnetic field is changing, it will surround itself with an electric field. So just take these two together and just think about it for a second. If I've got a magnetic field changing, it surrounds itself with an electric. Yeah. If the electric is changing, it surrounds itself with a magnetic. And if that is changing, it will surround itself again with an electric, and so on. Faraday to Maxwell, electric to magnetic, back and forth, back and forth.
So there's a coupling, basically, between the two.
Maxwell's equations were saying that electric and magnetic fields were inextricably linked. Changes in one created changes in the other. It helped explain so much. When Faraday moved his magnet, he changed the position of the magnetic field. And this triggered an electric field which caused electricity to flow through the wire. And when electricity passed through a wire, it wrapped a magnetic field around it, causing the compass needle to move. Using pure maths, Maxwell had unified electricity and magnetism and shown there were two aspects of the same thing, a single electromagnetic field. This alone would have guaranteed Maxwell's entry to the Scientist Hall of Fame. He could have rested on his laurels. But whether it was his natural curiosity or the long walks with Toby, he didn't stop there. He used his equations to test another of Faraday's ideas. Faraday had guessed that under certain circumstances, the electric and magnetic field lines could be disturbed by waves travelling along them, almost like ripples on the surface of water. Maxwell used his equations to show that the fields could fluctuate in time with each other and cause what Maxwell called an electromagnetic wave. He could even measure the speed of the wave.
This says the electromagnetic wave travels through space, and buried in here, he was able to extract the speed that the wave travels. And when he put the numbers in from things that Faraday and others had already measured, he worked out the speed, and it came out as a phenomenal 300,000 kilometers every second, roughly. And that, I think, is the moment of discovery, because he knew that people had measured the speed of light, which was 300,000 kilometers every second. Now, at this moment, you think, is this a coincidence? Or are these equations telling me something? Yeah. And, of course, they're telling you something. And what the message is, light is an electromagnetic wave.
This was a stunning conclusion. Maxwell had explained what light itself was. At the same time, he'd introduced something new to science: electromagnetic waves. And they were destined to change our planet. Problem was, he hadn't physically demonstrated the existence of these waves. It was all in the maths. Physical proof would have to come later. His equations were an astonishing piece of work, packed with radical ideas. Maxwell gave us a unified theory of electricity and magnetism. He solved the mystery of what light was, and he predicted the existence of these invisible fields that would directly affect our life. You know, that's difficult enough to grasp for a 21st century scientist, but what on earth did the Victorians think? The fact is, Maxwell was asking a lot from his peers. Invisible fields, undetected waves, dense maths. It's all a bit much for 19th century scientists. Ironically, Maxwell found himself in a similar position to Faraday, surrounded by sceptical colleagues and lacking the proof to vindicate his theory. But a jubilant Maxwell was undeterred. He wrote an excited letter to his cousin. I also have a paper afloat with an electromagnetic theory of light, which until I'm convinced of the contrary, I hold to be great guns. The guns may have fired, but it would be a while before they'd be heard. It took more than 20 years before a German scientist called Heinrich Hertz found physical proof for electromagnetic waves. When he was asked what practical use the wave had, he replied, "It's of no use whatsoever. This is just an experiment that proves Maestro Maxwell was right." How wrong he was, because Hertz had discovered radio waves. Marconi invented the radio, and since then we've been using them to spread radio and television all over the planet. But this was just the first in a long list of discoveries. Happy days are here again. Using higher frequency radio waves, we developed radar, which now gets used in everything from aviation to geology. Microwaves were discovered, which we use in cooking and when we use a mobile phone. Infrared is used in thermal imaging and in most TV remote controls. Ultraviolet's used in fluorescent lamps, security marking and medical research. X-rays have provided us with a valuable medical tool, but more recently in security. And gamma rays have been used to detect and treat cancer, and even to sterilise the food we eat. All these things are connected. Maxwell had shown that light and the colours we see are electromagnetic waves, but he predicted there would be more. Today we know that visible light is just a tiny sliver of a broad spectrum of electromagnetic waves. And by understanding and exploiting them, we've revolutionised our world. All thanks to equations Maxwell published 150 years ago. That was all part of a future that Maxwell wouldn't see. When he first published, people didn't understand him. You know, back in 1865, there was no sign, no evidence of these mysterious electromagnetic waves. Maxwell was asking people to believe that these waves could pass through empty space and affect things at a distance. It was just too much to ask. His equations were initially met with a bewildered silence. 19th century scientists were used to thinking of the world in mechanical terms. Physically tangible objects that could be touched, measured and felt. Flying in the face of that was Maxwell's theory, based on dense mathematics and visible fields and undetected waves. Many thought Maxwell's theory was a kind of abstract mathematical speculation, that he had strayed too far from physical reality, that he was, in essence, away with the fairies. Maxwell became convinced that he had to develop his theory of magnetism and electricity. Not long after that publication, he decided to pursue his own interests and resigned his post at King's. He was going home. After the lukewarm reaction to his 1865 publication, the comfort of Glen Lair was welcome. Ever industrious, Maxwell produced papers on thermodynamics and even topology. But always he returned to his electromagnetic theory, slowly refining it. After 6 years in the wilderness, Cambridge University approached him. They wanted someone to plan and run a lab in experimental physics. Despite all his achievements, Maxwell was third in line, after 2 other candidates had rejected the offer. In 1871, he left Glenlair for Cambridge, where he designed and built the Cavendish Laboratory, which would be responsible for discoveries that shaped physics in the 20th century. And as its first director, his open-minded approach set the tone for subsequent generations. I never try to dissuade a man from trying an experiment. If he does not find out what he wants, he may find out something else. The Cavendish lab would become a phenomenal success. It's within these walls that we discovered the electron, and later on, the neutron. Watson and Crick were working here when, in 1953, X-rays were used to show the structure of DNA. The Cavendish is now widely regarded as a centre of excellence, and it's produced 29 Nobel Prize winners to date. But every summer, Maxwell returned to Glenlair, patiently working out the full implications of his electromagnetic theory of light. In 1873, Maxwell released A Dynamical Theory of Electricity and Magnetism. The intervening years had allowed his colleagues time to digest his theory, and it was starting to gain traction. But he wouldn't live to see it vindicated. When guests were visiting Glenlair in 1879, Maxwell found that he could barely walk down to the river. Such was the pain. The pain was in his stomach. In October of that year, he was diagnosed with abdominal cancer, given a month to live. Maxwell was just 48 when he received the news. He knew his mother had died at the same age, from the same disease. Nevertheless, he accepted his fate with a calm stoicism that had defined his life. Catherine nursed him as best she could. It's said that on his deathbed, Maxwell breathed deeply, and with a long look at his wife, passed away. James Clerk Maxwell died in November 1879. He was buried in Parton Kirk, his childhood church, just a few miles from his beloved Glenlair. He lies on a modest grave next to his parents, and 7 years later, Catherine would be buried next to him. Apart from a plaque outside the cemetery, there's nothing to mark this grave as different from any of the others. There's no list of grand achievements. It's just simple and modest, like the man himself. A visitor could be forgiven for passing the grave without a second glance, but for some, this is a special place. There's a story that's told around Parton Kirk. Shortly after the fall of the Berlin Wall, 2 buses arrived, and people filed into the graveyard. A curious local asked who they were. They were, they said, Russian scientists who had travelled to visit the grave of Scotland's Einstein. You know, Maxwell died at a relatively young age, 48, which even by the standards of his day was an untimely death.
You just wonder, you know, given the achievements that he had in his lifetime, what he would have conjured up if he'd lived, if he was 60 or 70.
Maxwell may not have been fully appreciated in his time, but in the decades following his death, scientists started to recognise his genius. Eight years after Maxwell's death, Heinrich Hertz discovered radio waves, proving beyond doubt the existence of electromagnetic waves. The rest, as they say, is history. Over a century later, these waves have changed our planet and are part of our everyday lives. But focusing on the technological results of his work diminishes its importance, because he changed the way we understand reality itself.
Before the work of Maxwell and of Faraday, just before on the experiments, we understood the world in terms of springs and cogs, a machine-like world, and that machine-like world was pretty primitive. What Maxwell's work showed is the way that we understand the interaction between material bodies is via this idea of a field, not the sort of field we're standing in, which is not a green field, but something that penetrates space and which really governs the way that the world behaves.
Maxwell helped overthrow the mechanical model of the universe that physicists had held since Newton, and issued in a new era. We now think of all the forces in the universe interacting through fields, rather than direct physical contact. This was a crucial shift in our understanding, prompting Einstein to say, one scientific epoch ended and another began with James Clerk Maxwell. Which is, perhaps, why he's still revered by scientists today.
This meeting we're having here in Edinburgh today is very special. We're celebrating the 150th anniversary of Maxwell's publication of his equations of electromagnetism.
Some of Britain's finest scientists gather at an event to remember the life and work of James Clerk Maxwell.
Maxwell is all around us. Every single piece of technology that's around us today, computing, fiber optics, cameras, mobile phones, everything depends on extensions of those Maxwell's equations. Without those, we wouldn't be where we are today. Even the internet doesn't exist without them. Maxwell changed the way we think forever.
You can't overestimate his contribution, his influence on everything, both practical and theoretical. He is the most remarkable Scot, intellectually, that has ever arisen. No question about it.
In terms of the sequence of sort of great men of physics, starting with Galileo and Newton, then comes Maxwell, and then Einstein, who said that Maxwell was the greatest physicist after Newton.
It's wonderful to be sitting in the audience of a meeting surrounded by Nobel Prize winners, the great and the good. There's a sense of shared excitement that it's unapologetic geekiness that, you know, however much, the people like Peter Higgs and, Nobel Prize winners, we are still in awe of this giant of physics.
And having got to know the man, I can understand why.
I can't blame people for not knowing about James Clerk Maxwell. This is his difficult stuff. I just think that given the breadth of his discoveries and the sheer impact they've had, that it's a travesty that Maxwell's name's not up there with Newton and Einstein as one of the greats. Maxwell is Scotland's Einstein, and we should remember him as such.
What would it be like to take a journey into the mind of the world's most famous physicist? Go to BBC iPlayer to watch the animation short Inside the Mind of Professor Stephen Hawking. Here on BBC4, though, dredging up the secrets of the Spanish Armada and the Mary Rose in part one of Shipwrecks, Britain's Sunken History, next.